Hello friends, welcome to Susan and John MATHTUBE. This is the fourth lesson in the exam preparation series, and these videos are meant only for the first year engineering students who are studying in TU affiliated colleges. And as usual, how to use the video lessons effectively. And I'm sure you know all the points, but still you can read the points. So I hope you're ready with a pen and a paper. So let's start. And today we are going to learn about maxima and minima of functions. I'm sure that you learned a little bit of maxima minima in your class 11 or maybe in class 12. And that was maxima minima in one variable. Okay, so I'll give you the classification because once we classify, it will be very easy for you to identify the question. And one more thing, if you inspect your past question papers, you'll see maxima minima question in all the past paper questions. And it's a 5-mark question. So remember, this topic is extremely important. Okay, so we have function in one variable and then function in two variables along with a condition. That means a function will be given in two variables and a condition will also be given. But don't worry, it can be transformed into a function in one variable. That means with your class 11 or 12th knowledge, you will be able to solve such problems. And another one, very important, that is function in three variables, but two conditions will be given. Again, the good news is all you need is your class 11th and 12th knowledge to solve such problems. Let's go for the logic behind function in one variable. I hope you remember dy by dx. First of all, let's consider a function y equal to f of x, and remember dy by dx gives the slope of tangent to the curve y equal to f of x, and that slope will be at any point. Okay, and the second derivative gives the bend in the graph. Okay, I'll make it clear. So let's say this is the graph of a function, and you can see that this graph is tangentiable everywhere. At every point you'll be able to draw the tangent, and the slope of that tangent line will be given by dy by dx. And if you want the slope at this particular point, all you have to do is substitute the values of x and y in dy by dx. And the second important thing, that is the second derivative gives the bend in the graph. Now look at this. Let's say a graph is increasing, but let's say suddenly the rate of increase changed. That means the graph will bend. And if you want to know about the bend, all you have to do is to use the second order derivative. And now look at this. Let's say a temperature graph. So the temperature was decreasing, and suddenly let's say it rained and the temperature went down. See, another type of bend. So there are two types of bend. One is upward bend and one is downward bend. And the second derivative will be positive if you have an upward bend, and the second derivative will be negative if you have a downward bend. Okay, now I want you to imagine a rough graph of the function y equal to f of x, and I want you to notice one thing. At the maximum point, which corresponds to this in the x-axis, and at the minimum point, which corresponds to this in the x-axis, the tangents are parallel to the x-axis. And you might have learned, if a line is parallel to the x-axis, then slope will be 0. But slope is dy by dx. So what I'm trying to convince you is, if you equate dy by dx to 0, we will be able to extract the maximum as well as minimum points. Now let's go for the method. So the process is like find dy by dx and d square by dx square. That's number one. The next thing you have to do is you have to solve the equation which you get by setting dy by dx equal to 0 and find x. I told you when you solve this equation, the values which you get, that is the x values, will correspond to maximum or minimum. We don't know whether it's maximum or minimum, but it's for sure it's an extreme point. And now what we do is we will calculate the bend. You might have noticed at the minimum point the curve tends to have a upward bend, a positive bend, and at the maximum point the curve tends to have a downward bend. So we calculate the bend. So if the bend is positive, then x corresponds to minimum, and if the bend is negative, then x corresponds to maximum. Okay, that's it. The logic is really easy. So you can see tangents parallel to x-axis at maximum minimum points, that is our dy by dx being 0, and you can see that bend is downwards in the maximum point and upwards in the minimum point, and that is our second order derivative. Now let's be more practical for the exam and let's work out one problem. So the question is find the extreme values. So extreme values means it can be maximum or minimum. So we have a function in two variables and a condition. So I hope you remember the classification. I told you the maxima minima which you learned in your class 11th and 12th is about one variable function. But now we have a function in two variables along with a condition, and I guaranteed you can convert it into a function in one variable. So let's give it a name, and the function, and using the function I can extract the value of y and substitute. Once you do that, it changes into a function in one variable, and if you want, and only if you want, you can simplify. Now look at this. Let's go for the procedure. So we have a function. Now the process is very simple. Find the first derivative and the second derivative. And I'm sure you're very good in differentiation, so you'll have no trouble finding the first derivative and the second derivative. Now let's move to step number 2. So we are going to solve a very simple equation here. Okay, so let's set df by dx equal to 0, and that gives me x is equal to 1. So that is a stationary point. Now look at this. This point can correspond to maximum or minimum. Till now we don't know whether it corresponds to maximum or minimum, but we know for sure this will correspond to either maximum or minimum. Okay, now let's go for the third step. Let's plug in this value in the second order derivative. We cannot plug in anywhere because I don't see any x over here. That means the value is 4 itself, and 4 is positive. That means we have a positive bend, and that implies this corresponds to minimum. Okay, that's it. So we found that x equal to 1 is a minimum point. Now remember, we started with a maxima minima problem in two variables. So finding x is not enough. A point in two dimension means it will be in the format x comma y, and It's very easy to find. Use the condition. So we found the minimum point. Now for the minimum value, what you do is you plug in this point in the given function. So we get 1 square plus 1 square and the value is 2. Okay, now let's go for one more question. And please note it important. It's very important. Okay, so find the extreme value. Extreme means it can be maximum or minimum. So we have a function in 3 variables and subject to the conditions. Okay, so they are going to give us more than one condition. Okay, there it goes, the conditions. I hope you remember this picture. I'll magnify it for you. So function in 3 variables and 2 conditions. And what did I promise? I told you you will be able to reduce it into a function in 1 variable. So let's try it. So let's give the given function a name, that is x square plus y square plus z square, and let's write the conditions. And from the first condition I'm going to extract the value of x and I'm going to put it in terms of z. And from the second condition I'm going to extract the value of y and I'll put it in terms of z. And now let's plug in all these values in the given function. That's it. Now it's a maxima minima problem in 1 variable. By the way, I hope you remember a minus b the whole square and b minus a the whole square are the same. So I'm just going to write it in the form. Yeah, this sounds better. It's not compulsory, it looks better. Now for those students who don't know the procedure, so I have number 1, number 2, number 3, and that's it. We will solve the problem. So if you want, you can simplify a little bit. If not, you differentiate directly. It's up to you. So the first thing is we need the first order and second order derivatives. So it's easy to differentiate. Something square plus something square plus z square, and you can open the bracket 2z minus 2 plus 1 by 2. Okay, and on simplification we get this. Now let's go for the second order derivative. And now what should we do? Equate dy by dx to 0, but we don't have dy by dx in this problem, so equate the first order derivative to 0 and solve. Yeah, we got the value. And now I am 100% sure this is an extreme point. I don't know whether it's maximum point or minimum point, but it is extreme. So to confirm, what we do is we will plug in this value in the second order derivative. That's step number 3. You can read this step. So I have the second order derivative. The second order derivative is already a constant. There is no z here, so we cannot plug in anything. So this is going to be positive forever. You plug in any number, it's going to be positive. That means z equal to 2 by 3 corresponds to a positive bend, or rather we are at minimum point. Okay, but this was a function in 3 variables. That means a point will be in the format x comma y comma z. Okay, so let's plug in those values to find x and y. So we get x comma y comma z to be a minimum point. Now what do we do next? Yeah, the extreme value, the minimum value. So for the minimum value, what you do is you plug in this point in the function. So you're going to get 1 by 9 plus 4 by 9 plus 4 by 9, that will be equal to 1. Okay, moving ahead. So the question is, find the minimum value of the function x square plus y square plus z square with conditions. So again, it means there are two conditions. Okay, the conditions don't look that friendly, but let's try. So I'll put the question on the right side of the screen so that you can check it anytime you want. And I hope you remember function in 3 variables and 2 conditions can be reduced into a function in 1 variable. So let's start. Let's give the function a name, x square plus y square plus z square, and let's give it equation number 1. Let's call it equation number 1. Now look at this. We have this identity, y plus z the whole square equal to y square plus z square plus 2yz. And from here, what I did is I found y square plus z square because I am planning to write this in terms of x. And this is our first condition. And from here, I'll be able to extract y plus z. And that is 1 minus x. And now from the next condition, I'll be able to extract y into z. And now I'll plug in all the values in equation number 2. So this is 1 minus x and this part is minus 1 by x. Now look at this. This is completely in terms of x. Now let's replace this part with this quantity. Okay, so like I promised you, a function in 3 variables plus 2 conditions can be reduced into a function in 1 variable. Now all you need is the knowledge you had from class 11 and 12. So what is the procedure? First find the first derivative and second derivative. You can look at the right side of the screen. I have the method step number 1, 2 and 3. So let's find the first derivative, and I hope you remember the derivative of 1 by x is minus 1 by x squared. And simplify. And now go for the second order derivative. And I'll keep all those things here. And now step number 2. Equate the derivative to 0, I mean this function to 0, and solve for x. Okay, let's multiply throughout by x square. I'm applying distributive here. Okay, a cubic equation. Don't worry, you can take a calculator and solve it. Don't waste your time solving for cubic equations without a calculator. Take a calculator immediately and solve it. And make sure when you use the calculator, you input 2 minus 1, 0 minus 1. And that's it. You get x equal to 1. So we have completed step number 2. Now look at this. We know that x equal to 1 corresponds to maximum or minimum. It's an extreme point. Now to find it, we go for step number 3. So look at this. I have kept the first order derivative, second order derivative, and our hero, the point on the right side of the screen, or let's say the middle of the screen. It's not the right side. and we get 4 plus 4 by 1 cube, and that's positive, isn't it? And if the second order derivative is positive, then x corresponds to minimum. That means our x is equal to 1 is the minimum point. And now we have to find the y value and the z value. So let's plug in these values in the condition. You can look at the conditions here. Okay, so let's plug in x is equal to 1. So y plus z will be equal to 0, and if you plug it here, you get y z equal to minus 1. So y is equal to minus z, and let's put it in here. Let's put this y value here and solve it. And since y equal to minus z, it will be minus or plus. So the points are, so take a look at this, x equal to 1, that is fixed. Now if y equal to minus 1, then z equal to 1, and if y is equal to plus 1, then z equal to minus 1. So we get these 2 points. But the question is find the minimum value. So let's input all these things in the function. So we get 1 square plus 1 square plus 1 square is equal to 3. Okay, now let's move ahead to maxima minima in 2 variables. So let's go through the theory in a really fast manner. So let u equal to f of xy be a function in 2 variables. Now look at this. The conditions are not given. There are no conditions at all. So what you do is you find fx, fy and something called delta. That is this quantity. Now you are asked to solve these 2 equations. And remember, when you solve this, you should write the points in the form x comma y. I made it clear here. And then you take the points one by one and put it in delta. If delta is positive, then the point is qualified and it will be extreme. Extreme means it can be maxima or minima. And now the last test. Now what you do is you take this point and put it in the second order derivative. If you get positive, then it's a minimum point. If you get negative, then it's a maximum point. So let's try one question with that method. So the question is, find the extreme values of f of xy equal to x cube plus y cube minus 3xy. And like I told you before, there is no condition. So the question is a function in 2 variables and no conditions. So I have kept the question on the right side of the screen, and let's start with the given function. So do you remember the procedure? You have to find all the partial derivatives you can. Fx, that means you differentiate partially with respect to x. Then fy, that is you differentiate partially with respect to y. And next fxx, fyy and fxy. Now let's do one more thing. Let's calculate delta. I hope you remember the formula for delta, fxx fyy minus fxy the whole square, and that will be, here's our fxx and fyy, so 36x into y minus 9. Now let's solve the equations. Fx equal to 0 and fy equal to 0 simultaneously. So I have kept all these values on the right side of the screen. Take a look at this. Fx is 3x square minus 3y. Fy is 3y square minus 3x. So we are equating it to 0. Now we have to solve simultaneously. So from the first equation, I'm finding the value of y. Now what I do is I'll plug in this y value in the second equation, and that gives me x square the whole square minus x equal to 0. That is, and take x common. So okay, now tell me, if someone tells you a into b equal to 0, so what does it imply? It implies either a will be equal to 0 or b will be equal to 0. Now you have a into b equal to 0. So what does it imply? It means x equal to 0 or x cube minus 1 is equal to 0. Anyway, we get x equal to 0 and x equal to 1. Okay, now take a look at the question. How many variables are there? 2 variables. So you have to find the y value. So if x equal to 0, you can take a look at this y value. Y is equal to 0 square. And if x equal to 1, y is equal to 1 square. So we have the required points 0, 0, comma 1, 1. So now tell me, what's the next thing to do? Yeah, delta. So delta is 36xy minus 9. So if you plug in 0 comma 0, we will get minus 9, which is negative. So this point is not qualified. And if you substitute 1 comma 1, the answer is positive. So this point qualifies. Okay, now we know that 1 comma 1 is an extreme point. Now what we do is we go for the second order derivative. You can look at the right side of the screen. Yeah, second order derivative with respect to x. Or if you want, you can take it with respect to y. Now let's plug in that extreme point. Yeah, it's positive. The point is a minimum point. Now the last part. For the minimum value, what you do is you just plug in this function, and you get f minimum equal to minus 1. Okay, now something more important. So look at this. I'll read the classification once more. Function in one variable. This is exactly what you learned in class 11 or class 12. Now remember, sometimes they will give you function in 2 variables but along with one condition. And be very happy, you can reduce this into function in 1 variable type. And suppose you have a function in 3 variables and 2 conditions. Again, be very happy, and this is very important also. This can be reduced into a function in 1 variable. And then what we saw is function in 2 variables, no conditions, strictly 2 variables. And then we have function in 3 variables and 1 condition, not 2 conditions, 1 condition. And in this case, you have 2 options. If you want, you can reduce it into a function in 2 variables. Some people prefer that. And if you want, you can use something called Lagrange's method. And that is exactly what we are going to do in the next video. This video was a short one, but very important one. In the next video, we will be working out problems based on Lagrange's method. And I hope you are working out the questions from your reference books and the past paper questions. And if you find the video useful, then please like, share and subscribe. Anyway, I'll be soon back with the next video. So till then, bye.